lecture videos. There we go. Okay. Now let's do it. All right, so welcome back, everyone. Today we're going to be talking about LLVM generation. We're going to rewrite our interpreter, or we're going to delete the interpreter and write a compiler. So the current state of the compiler is that we can parse binary expressions with precedence, and then we can print out what they evaluate to. But you did not sign up for practical interpreter design, so let's write a compiler. So the first goal for Echo is just to compile our files into LLVM. And after that, we want to pass the LLVM that we generate into Clang, which is the LLVM compiler. And Clang is going to give us a binary. And you might think that's cheating because are we really compiling? The answer is yes, we are really compiling. But that's also exactly what LLVM is designed for. Remember that it's a pseudo-assembly language, so it generalizes a lot of the things that lots of different hardware manufacturers do differently in their CPUs. So there's only one way of allocating memory, and there's only one way of dealing with registers and stuff like that. And then Clang is going to take your target, and it's going to recompile the LLVM into x86 or ARM or something. And that's like the reason that LLVM exists. Fun fact, when I originally did Purple, I started writing it as an x86, or a compiler to x86, and I was taking computer architecture here at the same time, so eventually I added MIPS to it. And when I wanted to add ARM to it, I was like, man, I'm doing like so much extra work to compile to all these three things, and it became a real hassle to write submodules for every assembly language that I wanted to compile to. And eventually that was actually what killed my first attempt at doing Purple, was that it was just too much work to maintain 3 assembly language generators at the same time. Even though I did have like an abstraction layer, it was just so much work. So when I restarted last semester, I decided to do an LLVM compiler. And so this is actually going to be our big turning point from ACWJ, because that's an x86 compiler. So if you go and look at his notes, it's very different when you look at his code generator, because he has a finite amount of registers, which means he has to write register allocation functions and stuff like that, and it's a big hassle. And why don't we just use the better language to compile to, right? And then yeah, so it's going to let us compile to x86, ARM, MIPS, RISC-V, whatever, which is very nice. One thing is that I'm not going to be teaching you LLVM in one go. We're not going to have like an LLVM class or 2 or whatever. We're going to learn bit by bit the different instructions we can use, and we're going to use more and more complex things as the compiler grows. There are a few core tenets of the language that are different from any assembly language you've ever used before, which we're going to go over. And if you aren't familiar with assembly or computer architecture, this lecture might be a bit overwhelming, but I suggest you go watch lecture 0, where I talk about the basics of assembly language. So, LLVM basics. The first one is there are no registers in LLVM. Instead, we have virtual registers, and there are an infinite amount of them. So when you define a virtual register, you can only declare a value for them, when you declare them, you can only define them once with one value, and use the equals operator for that. And we're going to look at an LLVM program in just a second, so this is going to make more sense. But after that, you can only ever update their value with the store instruction. Our compiler is going to name virtual registers with numbers, so you're going to see lots of %, which denotes a local variable. Yes, there are locals and globals in LLVM, it's really cool. And then you're going to see a number afterwards, and that means it's a virtual register. Cool thing is you don't have to use numbers. You can give them names. You can use underscores and various other kinds of punctuation. and letters and whatnot. And if you want to handwrite LLVM, which nobody really does, although that would be a cool exercise. Yeah, you can name your registers whatever you want, and that way they act a little bit more like high-level variables that you're familiar with in high-level programming. The next thing is that LLVM is strongly typed, which means that every object in the language has a type at all times, and the compiler expects you to also know the type of whatever you're dealing with. So you always have to specify explicitly. For quite a while, we're just going to be dealing with integer types, and so those are denoted by this lowercase I. You put a number after them. These are the ones we're going to see most. So I1, that's going to be your Boolean. I4, that's going to be your short. I8 is a char. I32 is an int, and I64 is a long. But the cool thing is that you can actually have any bit width you want, which is really cool. I mean, you can do like built-in big integer stuff like what Python does, but you don't have to do any string stuff. So LLVM handles that for you, which is really, really cool. And then another thing is that LLVM lets you define functions and hook into the C standard library very easily. Handles all the linking for you. It's very nice. That's awesome because we don't have to explicitly deal with stack memory when we're calling those functions, although we are going to be talking about dealing with stack memory. And so in this first chunk, we're going to see what it looks like to hook into printf. So that'll be cool. So let's look at some LLVM. This is what we call the program preamble. So if you've written MIPS or any other assembly language, you'll know that lots of our programs always have preambles. Sometimes they're defining global variables that we'll use, or global values that we'll use over and over, or macros or something. In LLVM, there are some things we need to have, and there's some things that are nice to have. So first things first, in this first line here, you see semicolon module ID equals examples test 1. Semicolon denotes a comment. And module ID, that's just some flavor that Clang will spit out if you compile C with it. Oh, that's one thing. If you're having trouble with your LLVM generation, just pass a C file with your expected behavior into LLVM and use the emit LLVM option, and it'll spit out LLVM for you, and that way you don't have to go digging through documentation. We've got the source file name, kind of the same thing as module ID, but it gets more complicated when you do includes and stuff like that. You have your target data layout. This one is a doozy. This one I suggest you just compile a file with Clang because it's probably going to be different on everyone's machine. But basically, the data layout is explaining to the compiler what the kind of memory architecture of your RAM and your CPU looks like. Your target triple, that is another thing you should get from Clang if you're not sure. In my case, it's x86-64, which is the assembly language to compile to. We've got, and then Linux GNU, that's just, a bit more specification on what our compiled x86 should look like, because sometimes it's different between operating systems. We have this @printint f string. So the @ symbol, that is how we denote global variables or global values. Although they can be variables, you can do rewritable values up in the globals, but don't worry about private or unnamed adder, but constant makes sense, so this value should never change. And we see 4x I8 in these brackets right here. So this is a string, as you can tell by those quotation marks. And so we are telling it that this value right here is 4 8-bit integers next to each other, which those are characters, right? And we've got a percent. We've got a %d. That's our first two characters in the string. That is, if you've ever done printf in C, if you want to print out an integer, use %d for a decimal print. that \0a, that is the code for new line, and then \00, that is our null terminator. So what this string says is, if we're using it as an f string for printf, we're going to do %d and then a new line. So that's that. Don't worry about the align statement. We'll talk more about that later. And then finally, we have this define statement at the bottom. So again, don't worry about DSO local, but I32 is our return type. Global reference, 1 second. We call it main. This is our main function. One thing that's cool about LLVM is that it's got functions built into it. This is why I said we're not going to have to worry too much about stack memory stuff, because it's going to do that for us. Question?
What's the C prefix again in this string?
Don't worry about that.
Okay.
Not important. But you always have to do it, so just do it. So this is the guts of a program. This is all inside of a main function. And up at the top we see, we're just going to pretend that this is an expression that we've compiled. We have 2 + 3 × 5. So just take a look at that, and we'll get each of these chunks individually. So the first thing that we need to do when we are compiling binary expressions is we need to allocate space for all the numbers we want to compute. So this is where it gets a little tricky, because if you did pass a program into Clang that was just, int main return, or printf %d/n 2 + 3 × 5. You can't turn off the optimization in the compiler that auto simplifies mathematical expressions for you. So it's already going to have 17 in there. 2 + 3 × 5, 17. So it's not going to do any of this allocate stuff, probably. It might, but it probably won't. But this is just from digging around through documentation that I figured this part out. But yeah, so the first thing we need to do is we need to allocate space on the stack. And it's kind of also a virtual stack. Just don't worry too much about it. And that's what these first 3 lines are. This is what this allocate statement is. It's saying, give me an I32 and align it to the 4-byte boundary on the stack. If you've done any x86 programming before, there's a good chance that you've had bugs dealing with stack alignment. MIPS is more resilient in my experience to those, but so just as a rule of thumb, whenever we allocate space on the stack, we always want to align it to the byte width of the type that we're allocating. And so we allocate for 3 integers, 2, 3, and 5. These next 3 statements, store, remember that's the only way you can update those values. So we've got store I32, that's our data type. We're going to store the value 2. And then you're going to see that we actually store it as a pointer, which is that I32 star. And we're going to store those into registers 3, 2, and 1. Again, it seems a little convoluted, but this is how I got it to work. And I'm sure there could be a better way to do it, but I think it adds some nice challenging complexity to how we're going to deal with everything. And then finally, we are going to load the values in registers 2 and 1 into registers 4 and 5. So while registers 2 and 1 contain pointers to the values 3 and 5, as seen by the second 2 store commands, when we load those pointers, we're going to get the actual value from them. This is our next little chunk. Remember, we want to multiply 3 and 5 together. So that's what the mul command is for. That NSW stands for no signed wrap. And so when we use the no signed wrap keyword, we're kind of going to enable, I would hesitate to call it error checking, but inside of the compiler, the LLVM compiler, if one of those wraps occurs, so if you've got two 8-bit integers and you multiply them, or you're multiplying like 256 by 256 or 255 by 255, that's going to go out of bounds, right? It's going to go farther than an I8 should. And what LLVM is going to do is it is going to instead return a poison value, which poison values are weird, and if you look up an explanation of them, you're going to find lots of conflicting information. It's best just to read the LLVM documentation and just see what it says about each instruction and how it deals with the poison values. But very generally, they don't raise any errors when you pass them into most instructions. They're just going to get propagated through your program, and usually those instructions that don't throw an error when you pass a poison value into them they're just going to spit out another poison value. And the general idea is that they just prevent undefined behavior, because if you just, instead of computing whatever value you were trying to compute with a value that's gone out of bounds or something, it's just going to do a hard stop and return poison, which is just going to stop your hardware from computing things that you didn't intend for it to compute. So poison values are weird. We will probably not end up dealing with them. I'm sure there's some inputs you could do right now at the end of this lecture that would mess up our compiler, but generally we're not going to have to worry about poison values too much. So we multiply the contents of registers 4 and 5, which contain the values 3 and 5. That gets stored into virtual register number 6. We are going to load the pointer that's in register 3, which points to the value 2, into virtual register 7. So virtual register 7 now contains the value 2. And then we're going to add the output of the multiplication, which is in register 6, and we're going to add that to 2, which is in register 7. Again, these are I32s, nothing special there, no signed wrap, nothing special there. And ta-da, register 8 has the value of the binary expression contained in it. So this one's a little more complicated, but here, this is what hooking into the standard library looks like. So that's what this call keyword is for. This I32 is the return type of printf. That I8 pointer, comma, ... that is the input type of printf. So it takes a char pointer, which if you've written C, you know that's a string. And then it takes var args, which just means as many args as you want to put into it. We make a reference to printf, which we're going to define in the postamble. Again, we've got this I8 pointer. We tell it that it's 4 characters long. Don't worry about why there's 2 chunks of 4 characters long in there. It's weird. Again, this is what it looks like if you just... this was all trial and error when I figured this out. I would write a C program, I would compile it to LLVM, and I would just copy the behavior there. And so far, it's working really well. So we tell it the width of our string, we give it the reference to print in f string, and then we pass in our I32%, which had the sum of 2 and 3 times 5. Don't worry about these I32 zeros. Again, just weird stuff that the compiler spat out and that I'm now regurgitating to y'all. And then after we call that function, we are going to return 0. Because if you don't write a return statement in your main function, or any function, it's going to just return 0 in C. And that's basically it. I will show you the postamble in a second, but it's not super important. So we've looked at an LLVM program, and our goal is to traverse the abstract syntax tree that we can already generate And we want to use that traversal to generate programs like what we just saw. So let's take a look at the changes we need to make to accomplish this. So I'm going to go to echo.py. I'm going to pull up the notes on my screen. All right, so let's look at it. You'll probably notice that all of our interpreter code is gone because we're not interpreting anymore. Instead, it's been replaced by this call to generate LLVM, and we pass our parsed AST into it. That sounds like what we wanted to do. So, I don't need that. So let's look at this function. Let's look at the whole file, translate.py, which I put into the generation folder. So the first function call we've got in here is this translate init. It's nothing too special. Basically what it's going to do is we have all these global variables defined up here. LLVM out file, that is going to be the file that we're printing our LLVM to. Interesting note, LLVM has two forms. It has the text form, like what we just saw, but you can also compile to a binary. But honestly, why would we waste time doing that? We can read the text, we can debug the text, so we're not going to worry about the binary output. We've got this virtual register number, which is going to hold on to the last used virtual register. Because remember, if you assign to a virtual register with the equals operator, you can never do that again for the same virtual register. I'm going to say VR from now on. I think we'll understand it. LLVM free register count, we're going to get into that in a second. And then LLVM loaded registers, we're also going to get that into a second. But we just initialize these values here. We open up the out file. I've added a option to the argument parser to take in the name of an output file. Okay, so that's translate init. And then we have this adjacent LLVM file, and from that we're going to call LLVM Preamble. So let's take a look at that real quick. This should look very similar because it's what I showed you right at the beginning of the LLVM section. We have our module ID comment, which again, it's a comment, so we don't really need it, but we want to try and copy Clang as close as possible because Clang is a good compiler. We have our source file name. We have our target data layout. That's my target data layout. Again, you should probably run Clang print target triple, and it'll show you your data layout and your target triple. We define our printed f string. We have function adders, attributes. Again, another comment that you don't have to worry about. And then we've got our define statement for main. This #0, that is kind of connecting main to these attributes, and we'll look at that when we look at the preamble. Let me see, are we doing? Okay. So next thing that we do is we call this stack allocation function. So this is going to generate the alloc statements that we need, but before we do that, we need to determine how many alloc statements we need, what data types they're for, where they should be aligned, etc. And from that, we get this we get those values from determined binary expression stack allocation, same file. So it's going to seem a little weird right now because we only have one data type, and I picked I32 because it's a good one to just start out with. So you might be thinking, why don't you just traverse the AST, add up all the space you need, and then subtract 4 from it until you get to a point where there's no more space to allocate. We could do that right now, but I'd rather engineer ahead so that we don't really have to worry too much about it. This is a recursive depth first search to look at the entire AST and compile a list of all of the possible values that we'll need to allocate for. So if the root that we pass into it, if that has any children, we are going to recursively descend that child, get the answer that they need, get the list of variables to allocate for on that side of the tree. We're going to do it for the right side, and we're going to return the combination of those two lists. But if there's no children, then we're going to make this thing called an LLVM stack entry, which that's just a new class that I defined in echo/generation/LLVM stack entry.py. And it's going to store a register number to assign our allocate statement to, and then it's going to hold the byte width of our numbers. And again, we only have I32s right now, but later on when we add more integer types, this is going to be very useful. So it takes in an LLVM value. Have I gone over LLVM values yet? No, of course I haven't, because this is the first LLVM lecture. Let's take a look into LLVM value real quick. Basically, because LLVM is more complicated than other assembly languages, statements in LLVM can return many different kinds of things. So I wrote this abstraction class that takes in an LLVM value type, which can be either none or a virtual register. And I just wrote basically a wrapper around that, holds on to the type that you give it, and then it also holds a value for that given type. So if we give it a virtual register type, it's going to expect an integer as its value, and that's that. So we tell it we're making a stack entry for a virtual register, and we're just going to give it the next available local register, which you can see right here. It just adds one to the latest virtual register that we talked about, and then it returns that new one. And these free registers that I talked about, those are, you remember we did %1 equals allocate, %2 equals allocate, %3 equals allocate in the examples that we saw. Those at that point in the program would all be considered free registers because they don't have values stored into them. Or at least that's the name that I gave to them, is free registers. And so we just have this free register counter to tell the compiler how many registers do I currently have that I can assign values to. And I wrote this little function that, again, updates the count because sometimes we'll need to subtract them eventually. And that's it. And we return a list containing the new LLVM stack entry. So again, this seems a little complicated for what we need right now, but it's going to help later. So we're back in generate LLVM. We've determined the binary expression stack allocation that we need, and that spits out a list. And we pass that straight into LLVM stack allocation, this function right here. So for every entry in the LLVM stack entries that we get, we are going to print out %, because that's our local variable. We're going to print out the integer value of the register that we assigned to that LLVM value, because that contains the register we want to assign to. We print out allocate I32, and then we align it to the byte width of our data type, which again is just an I32, but it'll get more complicated later. It's going to do that. That's going to generate those first 3 lines of our main function that we saw, those 3 allocate statements. And next, we're going to do this thing, AST to LLVM. So this is where the logic of the interpreter is kind of isomorphic to the logic from the compiler. Again, this is another recursive descent. algorithm, but instead of computing values inside of this algorithm, we're going to be generating instructions to compute values. So we've got a left virtual register and a right virtual register. These are going to contain whatever LLVM values we get from the left and right children of the current node. And again, this is a depth first search or traversal. So if there is a left child, go traverse it and give me the virtual register. And if it's got a right child, traverse it, give me the VR. And after that, we've got our left VR and our right VR. Let's consider the example where we have a very simple AST that's just a addition node with a 2 and a 3 on the left and right children. So first thing that we're going to do, I would say 2 is the left child. So we pass in our AST, root is the plus node. We're going to traverse that left child, which is our AST node that contains the value 2. And in the 2 call, it has no children, so we're not going to do that. It's not a binary arithmetic token, which I just defined that. But it is a terminal token, and it is an integer literal. So we're going to store a constant. Let's look at that. LLVM store constant. And the value that we pass into it is just the number value. So in this case, it would be 2. So what this does is we are going to write out a store command. We're going to give it I32. We're going to store the value that we provided in this function. And then after that, we have to give it the pointer to a register, or a register that contains a pointer that we allocated. So this is where those allocate statements come into play. We're going to get that register number from this update free register count that we looked at. We're taking one away because it's not free anymore now that we've stored a value into it. And that function is going to give us the value of that. And then we're going to return an LLVM value that is a VR with, here, let's look back at the example real quick. So remember, we've got 1, 2, and 3. Those are our free registers. And then just because it's easier to do it this way, I started from the backwards down. So the first register we store into is the latest free register, which in this case is 3. You can see why it's easier to just use integers to name everything, because you can increment and decrement them instead of keeping a list of like string names, which gets complicated. So that's what this code is doing right here. We get that free register count that we just subtracted from, and we add 1 to it because we want that last value that we used. We could just store this into a value, and I don't know, I just did it this way because, don't ask me why. Okay, so that was in the case where we were looking at the plus and then the 2 and the 3, right? That was our AST. So after that, we've returned that LLVM value. So we're back up here in the plus level of recursion. And we're going to look at its right child. And the right child is the 3 value in our AST. And again, it's not a binary arithmetic operator, but it is a terminal and it is an integer literal. So we're going to store it this time into the first free register that we allocated. It's going to return that back up here on the plus level. And so now we've got a left VR and a right VR. And those are the virtual registers that we've stored the pointers for our values that we need into. We are going to look at our token. It is a binary arithmetic operator because it's a plus. And this is the other complicated function, the last one we're going to look at today. LLVM ensure registers loaded. So remember we've got these load statements here, which load the values from pointers into VRs. And again, slow me if I'm going too fast and I'm confusing you, slow me down, ask me a question. There's just a lot to cover today, so I wanted to get through it fast. So, when our compiler gets more complicated, it is going to become unclear on the surface level to see if the register that you're dealing with has been loaded or not. And so as a way to combat that from the start, we are going to keep a list of all of the loaded registers that we need at any given time. And the way we do that is we keep this global list of loaded registers, right? Yeah, global list of loaded registers. And for every register that we put into this method, in this case it's left VR and right VR, we want to go through our list of registers that we've ensured are loaded, and we're just going to do a quick linear search across them. In the event that we find out that all of our registers that we put in have been found, then we just return those same registers because they're already loaded, so we've ensured that they are. But if they aren't loaded, then this loop right here is going to step through the unloaded registers. It's going to generate a load statement for them. Again, $sign with this new register that we get, the next available local virtual register. We load an I32 into it, and from a pointer, and this is the virtual register number that contains the pointer to the value we want. So it's going to take that value from a pointer and it's going to load it into this new register right here. And then this is important, we have to append that new register to the list of loaded registers, the global list. And that's it. And we compile a list of these loaded registers and we return them. And right here, in the case that left VR and right VR are loaded, they aren't going to be overwritten because we just returned the same values that we took in because we saw that they were loaded. In the case that they aren't loaded, load statements will be generated for them, and then left VR and right VR will be overwritten with LLVM values that they contain the virtual registers that contain the loaded values instead of pointers to those values. Very, very, it's like kind of wishy-washy, right? It seems weird. I feel like I'm almost tripping over my words. But again, this is super important because later on in the compiler, when all of our stuff gets more complicated, when we have function calls, it's going to be very important to know whether or not we've loaded a value when we should have. So we've got our loaded values into left VR and right VR, and we're going to pass them into this LLVM binary arithmetic function that takes in a token and it takes in virtual registers. So let's look at that. It's very, very simple. We just step through all of our binary arithmetic operators, and if the token that we passed in matches any of them, we're going to add, subtract, multiply, or divide them. Let's just look at add real quick. We print out, we get a new register out VR to store our sum into. No signed wrap, because that's important. It's an I32 because that's the only type we have right now. And then we give it the left and right virtual register numbers. And that's going to add those values together, and it's going to spit them out into out VR. If we hadn't checked that left VR and right VR were loaded, we would get a compilation error or a runtime error or something. You would get esoteric behavior. So again, important that you load stuff. And then we return an LLVM value. It's a virtual register, and we give it this integer right here that tells you which register it is. Subtraction, again, super similar. In fact, it's the same except you write sub instead of mul. Add. Mul is also the same, but then division, we've got this udiv. It's unsigned because we haven't added in the unary negative operator into our language yet. And that's it. That's our binary arithmetic. So it's just going to get an out vr LLVM value. It's going to append it into a loaded register, because remember, the output of these binary arithmetic operators, they are loaded into their registers for us. We don't have to do any load statements. So we're going to append that to the global list of loaded registers. And that's the end. That's this return statement right here. So that's all that AST to LLVM does. Can everyone see that it's very similar in structure to how we wrote the interpreter? All right. If we've got an integer literal token, just return its value. If we've got a binary arithmetic operator, return the result of that computation. And that's our AST to LLVM function. It spits out an LLVM value. So in our plus 2-3 example, the return value of AST to LLVM is going to be an LLVM value containing the virtual register that contains the result of our computation. So it would be the value 5. And we call this print VR because we want to print out the number, right? If we did all this computation and didn't print it, there would really be no way of telling if the program worked or not. So we get this print statement, or print virtual register. We pass that into a function called LLVM print int. It generates this call statement that we looked at, and then we pass in our integer value to it. That one, super easy. And then we generate this postamble. So let's look at the postamble, because we didn't go over that earlier. We generate our return statement for the main function. We close the main function. This is where we're hooking into the C standard library by declaring this printf function. Clang will know what to do with it if it matches the name of a C function. These attribute statements, these are, remember in main, we have this #0. We have the same thing right here, #0. So this is just telling the compiler, I'd like my function to behave like this. Really the only one I would say worry about is opt none, which tells the compiler, don't optimize any of this. So when you compile the LLVM that you generate into assembly, you could open up the assembly, the x86 source file or something, and you could go and you would see a bunch of stack allocation. You would see storing constants into registers. You would see arithmetic operations, all the things that we just wrote, you would see converted to x86. Don't worry about these flags, but you need them. Don't worry about this, but you need it. This is why I would just kind of want to glance over these, because again, what you should do, go write a tiny C program that prints out the result of a binary arithmetic computation, and go and copy your postamble from that function, because it's going to be different on every machine. So if you just copy what I wrote here, and you're not on Ubuntu Clang version 10.0, you're probably going to get some errors that are going to be hard to debug. So just make sure, go generate your own postamble and generate your own preamble, and you won't have any issues, likely. And then that's it. And we're going to close this LLVM file, and we'll just do a little debug log statement right there. And that's it. That's our LLVM generation. So, yeah. So now our compiler behaves as it should, the way that we wanted it to at the beginning of the class. So let's go into echo, go into this checkout, and so let's see, cat examples test 1. 2 plus 3 times 5 minus 8, no, sorry, let me zoom in. 2 plus 3 times 5 minus 8 divided by 3. Remember, integer division, not float division. Let's do scripts, run, examples, test 1. Didn't throw me an error, so it should have spit it out to test1.ll. So let's do vim test1.ll. Look at that. This is the code that you just saw. We have, 2 plus 3 times 5 minus 8 over 3 or something like that. We allocate all of our space. We store a bunch of values to it. We load those values. We do some multiplication. We do some more loading. We do some more addition. We store, we load, we divide, etc., etc. And finally, we print it all out. So, is everyone kind of grooving with this? Again, very complicated lecture, but the code works. Code speaks for itself.
This has been the simplest part of it so far.
Say again?
This has been the simplest part of it so far.
Simplest.
This has been the simplest part of it so far.
Really? Wait, like this chunk of the lecture, or? Oh, okay.
LLVM.
Not the whole class. Okay, cool.
Not the whole class.
So yeah, that's that. One thing I would like to say, all of this stuff in the LLVM file, copy that, word for word. I don't care, because okay, don't copy and paste. I'd prefer you like write out the LLVM chunks of it, but the logic, the load function, like there's really no two ways to do that. So I would suggest just doing it, unless you want to write better code generation than I did. Question.
So what stuff should and shouldn't be copied? Like what's the stuff you specifically do want to throw out? So
The general rule is, if I say something is an implementation detail, don't worry about it. And you can copy it. Just go to the GitHub and copy it. In this case, I'm explicitly saying all the stuff in this file, copy it. My general rule of thumb is, if you're worrying about what you should or shouldn't be copying, then you're probably good, because if you're just copying for copying's sake, you're not going to be caring that much, I think. So again, all of the algorithms that I generally go over, take notes on those and then implement your own versions. But if I explicitly say copy it, go ahead and copy it. Or if I say it's an implementation error, go ahead, or implementation detail, copy it. Question?
So everything in the generation folder?
No, just this LLVM file. I mean, okay, your generate LLVM function, like what we saw here, that's going to be the same basically, right? But I'd like you to write AST to LLVM and determine binary expression stack allocation and translate in it. Those should all be, you should take notes and write them yourself. And one thing I realized is that I'm pretty sure I wrote 2 extra slides about this, and I must not have downloaded the latest version. So let me see what I wrote. Okay, yeah, so I had some questions over the weekend about the class. So one of them was, how should I utilize the lectures to help build the compiler? I suggest take notes during the lecture, highlight the big ideas of the algorithms, and then implement them on your own. I'm worried that my implementation may be too similar to Echo. So if you're studying the code from these lectures, and you're not looking at any of their sources, which is perfectly fine, your code is obviously going to look a lot like Echo, right? Because that's how I'm teaching it. And that's okay. The logic and structure is like, yeah, make it the same. It's fine. I just don't want you to literally copy, like literally Control-C, Control-V from GitHub into VS Code or whatever IDEs, right? I want you to understand what you're writing. So even if you write something that ends up looking very, very similar, I want you to understand. And in the event that I look at some code and I see it looks like they kind of just renamed variables, I might just like ask you about it or ask you to explain what you wrote to me so I can weed out any cheaters. Although I don't think any of you are going to do that, because why would you be taking a class that's not for credit if you were just going to cheat in it? It seems kind of ridiculous, right? And again, if I see something's in implementation detail, just copy it. It's fine. And one question I got was, I'm worried the code I write now will interfere with the code I write later, or that I'll have to do large refactoring. It's going to happen, guaranteed. Whenever you have a project that starts small and gets big because you want to handle more features, you're going to have to do some big refactors. And I've actually built in a couple refactoring weeks or lectures just because it's that important to get it right. So we're going to do our best to properly think ahead, like what we did today with the stack allocation algorithm. But there are going to be occasions, I guarantee it, where you're going to have to refactor your old code. And again, it's gonna make you understand your compiler better, which is a good thing. So, one more little slide about my philosophy on teaching. So when I started learning compiler design, the only thing I did really was I was reading ACWJ, and I was reading this blog called Mapping High-Level Structures to LLVM, and I was building Purple. My first attempt at Purple using its principles. And that allowed me to process everything at my own speed because it was just a side project. And I got to make improvements where I saw fit, which was nice. I really liked how unstructured it was. I liked how I could look ahead and I could see, if I just do like these two more boring chunks, I'll get to something cool like while loops or something like that. But not everybody does. I would like it if everybody took a similar path to what I did because, again, it was effective for me. But it would also be really cool if you guys just came to a lecture where I talked about code that I wrote. I mean, that's kind of what we're doing, but there's more of an agenda there. And the reality is that nobody would really come to that either. So the best combination is for you guys to listen to me talk about some code, but also write some code yourself. And so that's like kind of my whole goal with these lectures is just to combine the two, get as much of both as I can in there. And that's why I talk about the big changes that we make, and then I leave the rest up to y'all. And one thing, I was speaking about last week, my first week teaching with a professor of mine, and he told me that when an instructor teaches a course for the first time, they usually learn more than the students. And so far, that seems pretty true to me. Listening to the questions that y'all have and rewriting an old compiler of mine in a new language that sucks, it's teaching me a lot. So I'm having a blast. I hope y'all are. That's my general philosophy. So if that clears up any questions you have on how much you should be copying or not copying or whatever, I hope that does it. So, any questions on that?
Since I'm like rewriting it in an entirely different language that's quite a bit different, I think that generally tends to involve like having to understand what exactly it's doing, and then like even if the implementation kind of looks the same, would that still be sufficient, you think, just to?
I would say that yes, your logic and your structure is going to look very similar, and individual functions are going to look very similar, but again, if you're worried about cheating, if you're worried about copying, that probably means that you care about the right things. So I would worry less. And the people who aren't worrying at all, I would say worry a little bit more. So again, it's a weird line, right? Because there's no grades. I'm not really checking you as the semester goes, except for midterm and final. So it's a weird line, right? So again, if you'd like, just send me like your implementation and say, hey, does this look too similar? And I'll say yes or no. I'm not going to kick you out that instant because you asked me. So, but if you get to the end of the semester and you show me your compiler and it's like word for word what I wrote, then yeah, of course I'm gonna get a little, fine line, right? Fine line. We all get it. Okay. One thing I forgot to show you is compiling with Clang. So let me do that real quick. Cat test1.ll. Okay, we've got that. So this is going to take in that file that we just compiled with echo. It's going to pass it into Clang, and it's going to spit out a binary called test1. Let's see what test1 does. It prints out the number 15. Let me print out test1 again. Python 3. Let's see. 2 plus 3 times 5 minus 8. Integer division 3. 15. Okay. So Python agrees with our compiler and Clang and whatnot. So just wanted to show you that. And last slide. So this was a complicated lecture. I promise it's probably the hardest that we'll have for at least like a month, I think. The next hardest one is going to be adding functions, which we're actually going to be doing over the course of probably 3, maybe even 4 lectures. And after that, and in between, it should be pretty smooth sailing. Like the next lecture is going to be pretty easy, probably like half the length of this one. Until then, if you have any trouble or you're feeling overwhelmed, come to office hours. Remember, there's not really any deadlines. And once you get this groundwork out of the way, once we do this and next lecture, we really pave the way to add so many things. And at that point, like after our next lecture is we're going to be adding explicit print statements. So right now we just have one expression per file, and it compiles to something that has a print in it. Eventually we're going to add print statements next lecture. That lets us have multiple prints per file. And once we have those out of the way, we can kind of add in bits and pieces radially. So I'll be going into loops after that, but you don't have to do loops. You could do other kinds of operators or if statements or whatever. Like there's so many things you can do at that point. So remember that to earn the certification at the end of the semester, there are a set of required features that your compiler must have. So far, everything that we've gone over is required. But after we've implemented that and this next lecture, we're kind of 40% done with the required topics list. So that's cool. And again, after this, we're just going to open the door to add in syntax of your choosing or new features that you're coming up with on your own. So get excited, start thinking up ideas for your custom languages if you have those, or language extensions if you want to write a better Holy C or something. So that is the end of the lecture. Does anyone have any questions? Nope. Okay. Well, I'll end the stream. We've got about 15 minutes. And I can walk around and help people start